Okay, it's time to go ahead and get started. So today we're going to talk about shift registers and then also sequence detection. And both of these are important for assignments coming up. The shift register, as you'll see Tuesday when I talk about binary multiplication, it's part of your final project individual. Okay, because the shift register is hardware that's part of how you do binary multiplication. And then sequence detection, this is what you need to know to do lab 6. Okay, lab 6 is due a week from tomorrow, so Friday of next week. Remember, due tomorrow is lab 5, and hopefully you've got to start on that. And you should have time after the lecture and also the activity to work on lab 5 if you still need to. Okay. All right, but where we're going to start is with shift registers. And there's 2 types of shift registers. These are the acronyms, SRR and SLR. SRR stands for shift right register. And SLR stands for shift left register. And what's meant by shift right is that the data goes from most significant bit to least significant. So if shift right is data going from most significant bit to least significant bit, how do you think the data goes for shift left? Yeah, just the reverse. So shift left data goes from the least significant bit to the most significant. And if you think about it, it kind of makes sense, right? Because we think of the most significant bit being furthest to the left and least significant bit being furthest to the right. So if the data is going most significant to least significant, right, it's going to the right. And if it's going least significant to most significant, it's going to the left. Okay. So I have a couple of examples, one of each type of shift register, and I think the examples like illustrate the difference between the two. So this is the first example. It's a shift right. And just like any register, a shift register is either rising edge or falling edge trigger. Okay, so this first example, I got a shift right that's rising edge. And the second example, I got a shift left that's falling edge. You know, there's nothing special about the shift right being rising edge. It could be falling edge. Same thing with the shift left. It could also be rising edge. It just picks one to be rising edge and one to be falling edge just for example purposes. Okay. Now, also, you haven't seen this notation before, I don't think, where there's a rectangle with some squares. This symbol is for a register. The rectangle represents a register, and then each square represents a flip-flop output contained, within that register, right? Because as we talked about, registers just are multiple flip-flops. Right, so you see 1, 2, 3, 4, 5, 6, 7, 8. This is an 8-bit register, so that means there's 8 flip-flops. And inside each square, we're showing the output of an individual flip-flop. Okay, so let's say that this top rectangle here with our 1s and 0s, let's say this is the initial data. Okay, inside the shift register. Right, as you see, this is the most significant bit. Okay, also often a shift register will have an input that's labeled DR underscore IN or something similar. And N is for input, and then DR just stands for data writes. And what that means is whatever data we have on this DRN, that's the data that's going to go into the shift register. Okay, and when it's a shift right, that data goes into the most significant bit. And that data will go into the shift register as well as all the other bits shifting that we'll see in a minute at the time of the 0 to 1 transition of the clock. So, okay, when the clock transitions from a 0 to a 1 at this time, since this is a shift right, the data on the DRN, it's going to go into the most significant bit of the register, and then all the other bits are just going to shift over one place. Okay, and then this bit here would just fall off the face of the earth because there's no way for it to go. Okay. So you see, if this is our initial data, and we're doing a shift right, and we put a 0 on the DRN, this is what we're going to have after the clock edge. And so this is the data after the clock edge occurs, right? Because the shift happens at the time of the clock edge, and then after the data will, the new data will be there. Okay. So, any questions on the shift right example? Because if you understood the shift right, shift left is just the data is going the other direction. Okay, that the data in goes into the least significant bit, and the bits just shift the other direction. Okay, so this is our shift left register example. It's a falling edge trigger. The data that goes into the shift register when we're shifting left is on the DL input. And the time that the shift happens is on 1 to 0 transition of the clock, right? Since it's falling edge. So at this time of the 1 to 0 transition of the clock, this 1 that's on the DL in, that's going to go into the least significant bit, right? And then again, all the bits just shift one place over. And that 0 would just fall off the face of the earth because there's no place for it to go. Okay, so that's shift right, that's shift left. Any questions about anything up to this point? Okay, well, what do we use the shift register for? Well, there's a number of different things, but one common thing, and you'll see this when you take CPE133, is that you can use a shift register to either multiply or divide by a whole number power of 2. So for example, let's say we start out with this binary number, 1100. So if we treat this as a binary number, what is this in base 10? 1100. Should know this right off the top of your head now. It's a 12. Okay, 12 in base. So if I start off with the 12, right, 1100, and I do a shift to the left, one shift to the left and bring in a 0, I would get shift, right? Because I bring in this 0 and then I shift all the bits over one place. So what binary number is 11000? 24. Right? There's no 1s, no 2s, no 4s, and 8 and 16. So you see, by doing one shift left and bringing in a 0, we multiply by 2. And if I did another shift left, bringing in another 0, I would get 48. Right? So you see, you can multiply by a whole number power of 2 just by shifting to the left the appropriate number of bits. Okay? So how do you think we divide by a whole number power of 2? To the right and bring in a 0. Okay? So for example, if you started off again with a 12, right? Started off with 1100, and I shifted one place to the right, bringing in a 0. I would get 6. And if I did it again, I would get 3. Now to do it anymore, I need more bits, right? But if I had a bigger shift register, I just need more shifts to the left before I ran out of places for bits to be. And I could do higher division of power of 2s, but anyway, you get the idea. Yeah. You'll see, when you take CPE133, in addition to building that microprocessor that I've had you look at the diagram a number of times throughout the quarter, well, in addition to that, you also learn what's called assembly language programming. At the same time you're building that microprocessor. And at the end of the quarter, once you have the microprocessor all built, you program it with assembly language. For those of you that don't know, assembly language is code that's closer to the hardware. Okay, like you have commands in assembly language that like moves data between registers. And you'll have commands that do shift left and shift right. Like there's a command shift left, so many bits. And you'll be writing programs in this assembly language. And I think there's one exercise that you do in that class, one homework problem where you have to do a division by 4. Right? And this is the way you can do it, right? Just by shifting right 2 places, bringing in zeros. All right, so any questions about shift registers? Because we got one more thing to go over with shift registers before we start a new topic. But any questions up to this point?
So for the shift right register example, does it add an extra bit or does it just usually
It just shifts the bits one place. That's why it's called a shift register, because the new data comes in, but all the other bits that were there originally, they just move over one place. And then because there's no place for this bit to go, like there's not another flip-flop for it to get stored by, it just effectively goes away. You lose that bit. Yeah, but it's just that all the bits just get shifted. Any other questions? All right, well, there's this shift register called a universal shift register, because see, what we went over here is just, like basic shift register. But there's this device called a universal shift register that can do more than just shift right and shift left. See, these can shift left and shift right. That's a comma, by the way. It can also store, hold, and it can load data. And when I say load data, that's the same as a memory register when Q equals D, right? When we update the Q outputs with whatever's on the D input. So these universal shift registers, they can shift either direction, and they can store, and you can load data too. So here's a high-level black box diagram of a universal shift register. So, it's got a Q output just like a memory register does. It has a D input just like a memory register does. It's got a clock because all sequential circuits, right? All types of registers have clocks. It'll have a clear just like a register does. But what it has in addition is this input here, a select input, SEL. And you can see here that that select input is 2 bits. So with 2 bits, I can represent how many values? 4 values. Okay, so that select, based on what binary 2 bits are there, are selecting from 4 things, right? Because I can have 0, 0, 0, 1, 1, 0, 1, 1. Well, if you look on your table, every table should have a handout that has code, Verilog or system Verilog code for a shift register like this. So if you take a look at that handout, and I didn't write all the code that's on that handout because what's at the top, is code we've already talked about before, so it should be familiar to you. But what I wanted to focus on in this discussion is in that code, under the else, okay, under the else for the if, there's a case statement. Okay, so we have this case statement, within the if, under the else, and you can see that the case depends on input SEL, right? So remember, what goes inside these parentheses of the case statement? When that changes, that's when the case gets evaluated. So look, if our select input is a 1, right? If I put a binary 1, 0, 1. Well, it's gonna be this option right here, where Q is gonna be assigned whatever's on the D input. So you see, this is when it's loading. Right? This is when data on the D input would be loaded to the Q output, just like in a shift register when we, or excuse me, a memory register when we do enter. Enter and load, same thing. Okay. All right, but let's look at the next line of the case statement 2. Right. So when the select line is a 1, 0, Q is going to be assigned what you see here in braces. And look what's inside braces. These braces. Q 6 to 0. So remember that we give the least significant bit number 0, and then this is 8 bits. So the most significant bit would be number 7. So you see, when we put a select of 2 on this universal shift register, Q is going to be assigned bits 6 through 0, right? So it's going to be assigned these bits along with a 0 tagged on to the end of those 6 bits, right? Because remember we talked about what the braces do in system Verilog? Like, what do we call this when we have the braces? What are we doing here? Concatenate. And concatenate means you're just putting stuff together, right? Combining, joining. So you see what's happening here is it's taking these 7 bits and then it's attaching a 0 to the end. So effectively, what happens when you do that? When you take these 7 bits and you put a 0 over here on this side. Taking these bits and then I put a 0 on the other side. It's all going to fit within this 8-bit register. It's going to shift. Right? Which direction is it shifting? It's shifting. So you see, this is how in system Verilog you do a shift left. You do a shift left by using the concatenation. Okay, if this is shift left, what do you think option 3 is, where we're putting a 0 to the left of these 7 bits, right? Because this is bit 7, this is bit 1. So now I'm putting a bit over here. It's all got to fit within the same register. So that's shifting it to the right. Okay, so this is a shift right. Okay, now notice option 0 is missing from the case statement. And that's not a mistake. That was done on purpose. Why is option 0 when the select line is 0, 0, right? A binary 0. We don't have a choice here. Why is that? What's going to happen if I don't have a complete case statement? What happens if I don't have a complete if, like if I leave out the else? Yeah, it creates a latch, which is the memory, right? That's the storage. So same thing here. By leaving out the 0, that means that's the storage. That's when the hold happens. Okay, so you see, there's no option 0 because that's going to create the storage. You know, it creates a latch, which creates the storage. Okay, so that's your hold state. Okay, what else is missing from this case statement? What should a case statement have? What have you been told? Case statement should have a what? Default? Yeah, it should have a default, but we don't have a default here. And actually, this is one of the rare cases where you don't want a default. Because if I don't have a default, that means it's going to default to what? You're missing something and create. Just like we didn't have a 0, it created a latch. Yeah. So by not having default, you know, the word default, the default becomes the hold state. Okay, in a memory like this, that's what you would want. right? Because if you did put something here and you assign Q to something, you might be changing Q to something that, depending what the shift register is part of, what kind of system it's part of, it might actually do more damage. It's better just to keep what you have and change it to something that, because you don't know when the default's going to happen. If you change it to something where, whatever the shift register is connected up to, it, might cause bigger problems. So it's better just to stay with what you got in this case. Okay, so you see, sometimes a default can be a hold, like we have here. Okay. All right, so any questions up to this point? Because that's all. Now, there's an activity that involves a universal shift register, and I'll talk about that after, I talk about the next topic. But up to this point, are there any questions? Because we're going to switch gears and talk about something totally different, sequence detection next, if there's no questions up to this point. So everybody's okay? Okay, well, like I said, there's an activity on this, so that will give you some more practice, and hopefully really, after you do that activity, you'll have a good understanding of a shift register, particularly a universal shift register. All right, but now let's talk about sequence detection. And sequence detection, that's what Lab 6 is all about. Okay, because in Lab 6, you're going to build a sequence detector. Okay, you're going to build an FSM that will detect the sequence. In fact, it's going to detect 2 sequences. Okay. So the first thing about sequence detectors that do sequence detection is that there's 2 types. There's resetting sequence detectors, and there's non-resetting sequence detectors. And the definition of these is very important to be able to understand, okay? So I have the definitions up here. If you have a resetting sequence detector, and these first 3 words are very important, okay? After a detection. Okay, so after you've detected whatever sequence you're looking for, no prior bits can be part of a subsequent detection, right? So I detect some sequence. Once I've detected that sequence, any subsequent sequence cannot contain any prior bits. Okay, that's what resetting means here. Non-resetting, now, you all know what I mean by when I put these double dashes, right? I'm just repeating what's above. So I just didn't want to write the same thing. So, it's after a detection again. Okay, so if it's non-resetting, after a detection, prior bits can be used part of a subsequent detection. Okay, so that's the difference between the 2. Resetting, you can't use prior bits after you've had a detection. Non-resetting, you can use prior bits after you've had a detection. Again, this is key, after a detection. I'll come back to this, when we're doing an example coming up, because this is where people often make a mistake. Okay. All right. So as an example, okay, an illustration of the difference between resetting and non-resetting, I have this example here where we want to detect this sequence right here. Okay, we want to detect 1011. And here we have a string of bits. And, just like in a timing diagram, t equal to 0 is over here. And as we go left to right, time is progressing. So, we have a string of bits. First it's a 0, then a 1, then a 0, then a 1, then a 1, and so on. Okay. And we're looking at the string of bits, and we're looking for this sequence. Okay, if it's a resetting, you'll get a detection here, right? 1011. You'll get a detection here, 1011. You'll get a detection here, 1011, because all these detections do not involve prior bits of a detection. But now, when you get right here, okay, here's our 3rd detection of this sequence. Now, if I counted this 1 that's part of this detection, if I counted that with these 3 bits, that would be another detection. But with resetting, you can't do that. See, with resetting, you can't use any prior bits for a subsequent detection. So this 1011, if we're doing resetting, would not be a detection. We would only have 3 detections. This would not count because I'd have to use a prior bit to get that 1011. Now, if it's non-resetting, where I can use prior bits, okay, so in red would be our non-resetting. Well, I'd have a detection here, I'd have a detection here, I'd have a detection here, and I would have a detection here because with non-resetting, I can use bits from a prior detection, right, for a subsequent. So you see, for resetting, we'd have 3 detections. For non-resetting, we'd have 4 detections, the difference being right here. All right, so you see this here shows an illustration of what we're talking about up here with words. Does that make sense to everybody? Any questions? Okay, so the next thing, and you know, I mentioned this last class, because remember, last class we talked about FSMs, and you know, I showed you the format of the system Verilog code you need to model an FSM in system Verilog. And what did I say that class? What did I say about state diagrams? You always what? You just dive into an FSM writing code right away. No, first thing you do is a state diagram. So, you know, lab 6, before you even think about opening up Vivado, you have to have your state diagram for the sequence detector, okay? So I'm gonna show you how to do a state diagram for a sequence detector with this example, okay? That we're gonna look for this sequence, 1011, okay? Now, every state diagram has a legend. Now, most people in the activity last class, most people did include the legend along with their state diagram, but there was a few groups, I think it was 1 or 2 maybe in this section, there was 1 and 2 in my other sections also, that didn't put a legend. I took like a point off. But you know, you've got to have a legend. You know, when you do your final project, you'll see when I talk about it next week in more detail, you'll see that one of the things you're required to turn in with your final project is a state diagram. And you want to make sure that that state diagram that you turn in for your final project, it has a legend, right? Because if it doesn't have a legend, I can't read it, okay? So here's the legend for the state diagram for this example. Remember, like we talked about last class, the circle in the legend and also in the state diagram represents a state. Okay, and then you give your state a name. You can see I just used letters for my names here. Okay, and then like we talked about last time, what always goes right here inside the circle? Like, what do we call this? More output, exactly. See, this Z is the more output, right? Remember, more outputs go inside the circle because the circle represents a state, and more outputs only depend on what state you're in, right? If we had a mealy, it would be out here, okay? But this is the more. So Z is a more. Z is a more output. Now, what we're using Z for is that when Z equals a 1, that means that we detected this sequence. Okay, so when Z equals 1, sequence 1011 has been detected. Right? If Z is 0, that means we haven't detected sequence 1011. Okay. Okay, then we have by the curved arrow. And what does the curved arrow represent in state diagrams? Like, how do we go to one state to the other? Like, what has to occur? Here's a clue. What has to occur? Clock edge, right? Yeah. Clock transition. That arrow represents a clock transition, and then it's a conditional clock transition because there's something here. Remember, if it's unconditional, you won't see anything there. But this X, that's an external input. And that X represents a bit of our series of bits. What's that? Oh, thank you. Thank you. I broke my streak. Actually, this still counts because I didn't have to turn it that much. But thank you, yeah. Otherwise, the people watching this later wouldn't be able to see what I'm writing. So thanks. All right, so this external input represents a bit of the series of bits. So like in this example here, this is X. Right? It's the series of bits that we're looking for the sequence of or in. Okay. So you know our X would be changing, like it would be 0, then 1, then 0, then 1, then 1, and so on. Okay. All right. So let's go ahead now and let's create this state diagram. So state A is going to be my first state. That's where we're going to start. Okay. So since we're starting at this state, I don't have a sequence yet, obviously, because I haven't started. So Z will be a 0. Okay. Well, if I'm in this starting state A and I get a 1, if X is a 1, I'm going to move to state B. Okay, so you see, if X is a 1, I go from A to B because that's the first bit I'm looking for in the sequence. Okay, then when I'm in state B, oh, also because we haven't detected the sequence yet, we only got the first bit, Z would still be a 0 here. Okay. Okay, I'm in state B. If I get a 0, well, that's the next bit I'm looking for in my sequence. So I'm going to go to the next state. So a 0 takes us from B to C. And again, I haven't detected the sequence yet, so Z would be a 0. Okay, I'm in state C. If I get a 1, I'm going to move to the next state because that's part of the sequence I'm looking for. And again, I haven't detected the 1, 0, 1, 1 yet, so Z would be a 0. I'm in state D. And if I get a 1, I'm going to go to state E. And now in state E, I have detected the sequence I'm looking for, right? Because it took a 1, 0, 1, 1 to get there. So this is when Z would become 1. Now I got a detection. Okay. So that's the easy part of a state diagram for a sequence detector is, mapping out the path for a detection, right? Because you're just going to move from one state to the other if you get the right bit. The tricky part of doing state diagrams like this for sequence detection is determining where you have to go when you get a bit that's not part of the sequence you're looking for. Okay, so that's what we're going to do next. And what I like to do, because this helps me, okay, not everyone has to do this, but what helps me determine like where I need to go if I don't get the bit I'm looking for in the sequence is writing down next to each state what it took to get there. Okay, now state A, that's where we started. So you just start there. But to get to state B, we needed a 1. Right? To get to state C, we needed a 1, 0. And to get to state D, we needed a 1, 0, 1. Right? And then obviously to get to state E, you need the total sequence, right? You need the 1, 0, 1, 1. Okay, like I said, writing down what you need to get to a particular state, it's not necessary, but I think it's helpful for a lot of people. Okay. All right, so now let's think about what the state diagram is going to look like when we get a bit that's not a bit we're looking for in our sequence. So we'll start at state A, right? Because at state A, if we get a 1, that's the first bit in our sequence, so that's why we go to state B. But let's say we're in state A, we're starting, and instead of getting a 1, we get a 0. So instead of this being a 1, we get a 0, which is not part of the sequence we're looking for, right? So what are we going to do? We're in state A. Where are we going to go if we get a 0 as our first bit? Yeah, just stay in A, right? Because if my first bit is a 0, Well, I would just stay there until I get a 1, right? Because now maybe the sequence I'm looking for is going to start. Okay, but if I get a 0 to begin with, I'll just stay in A. Okay, does that make sense? Okay, so now, let's say we get a 1. So now we're in state B. But we're in state B, and instead of getting a 0, we get a 1. Right? So I'm in state B, and I don't get the 0 that's part of the sequence I'm looking for. I get a 1. So, you know, it took a 1 to get the state B, but now let's say I get another 1 instead of a 0. So if I get this, what am I going to do? Would we go back to A? Does anyone have any other ideas? What's that?
The next bit.
Well, you got to look at it a bit at a time. So we're just looking at this bit here. Okay, so to get to state B took a 1, right? So this 1 took us to state B. So if we get a 0, we're going to go to the next state because the 0 is part of the sequence we're looking for. But if we're right here, we're at state B, and instead of getting a 0, we get a 1, right? We're going to have this, right? A 1 and then a 1. What's that?
Reset like it's checkered, so you have like that 1 is the first one, so you just go back to B.
Yeah. How many people agree with that? That we would go back to B? Yeah, because see, if we get another 1, that's what it takes to get to B is a 1. So, you know, if you get a 1 and another 1, you know, the next bit here could be a 0 that takes you to C. Right? So if you're in state B and you get a 1, well, since it took a 1 to get to B, if your next bit is 1, you would just stay there, you know, waiting for this 0 to happen. Does that make sense? All right, so yeah, you would just stay here at B if you're getting a 1. Okay, all right, so now we've got, let's say we get a 0, right? So we get a 1, then a 0, so now we're at state C. Right, we're at state C. If we get a 1, we move on. But what would we do if at state C we got a 0? Meaning that we'd have 1, 0, then a 0, right? Because it took a 1, 0 to get to C. But now if we get another 0, where would we go? Where would you go? I heard it. Okay. Yeah, we go back to A. Why would we go back to A? Say that again?
For a full reset.
Do you mean start over again when you said reset? Yeah. Would we have to start over again? Because it, you know, it took a 1, 0 to get to C. Now, if I get another 0, I got 1, 0, 0. There's no 2 zeros in a row in the sequence we're looking for. So if you get 2 zeros in a row, you might as well start over again, right? Okay. So yeah, we go back to A when we're in state C if we get a 0. Okay. So now let's say we're in state D, right? To get to state D, it took a 1 when we were in state C, right? So to get to state D, we need a 1, 0, 1, right? These first 3 bits here. And of course, if we're in state D and we get a 1, we go to E because that's a detection. But what if I get a 0 when I'm in state D? Meaning I have 1, 0, 1 because that's what it took to get there. But now if I get a 0 after that 1, 0, 1, where would you go? Yeah, why back to C? Yeah, I go back to C because with that 0, now with these 2 bits, that could be part of a detection, right? It takes 1, 0 to get to C, so I would just go back to C from D. Little tricky. Like I said, I think writing what it takes to get to a certain state, I think that helps, right? Because you can look at, well, what it took to get to that state. And then if I don't get the bit I'm looking for in my sequence, okay, well, what does that mean? Now, I have a question for everyone. And that's, we're going to finish this. We're not done yet. Okay, we're gonna finish it, but up to this point, okay, up to this point where you see green and black, is this a resetting or non-resetting? Is this state diagram for resetting or non-resetting? How many people say resetting? How many people say non-resetting? How many people don't know? How many people think this is a trick question? Why is it a trick question?
We haven't finished, so you can't really tell.
Not quite, right? What do the definitions say up there about resetting and non-resetting? What's the first three words? After a detection. Are we after a detection yet? I mean, this is a detection, but we're not after a detection yet. So it's a trick question because what we have right now is for both a resetting and non-resetting. The state diagram for resetting and non-resetting is different after you have a detection. So after state E, right? After we have a detection, we're going to have differences based on what type we have. But before you have a detection, there's no difference between a resetting and a non-resetting state diagram. They're both the same. Okay, that's why I said earlier, these three words are very important because the difference of these don't come up until you have a detection. Okay? All right, so we're going to finish this state diagram first for a resetting. We'll do it in red. Okay, so red is for reset. Okay, so again, after a detection, so here's our sequence that's been detected. And if it's resetting, it means you can't use any prior bits, right, for a subsequent detection. So let's say after our detection of 1011, we get a 0. So where would we go from state E? Did I hear C? What does it take to get to C?
10.
And remember, for a resetting, we can't use any prior bits. So actually, you're a little bit ahead. That's going to be when we get to non-resetting. But for resetting, where you can't use the previous bits, it would be what? A, yeah, you just have to go to A, the starting point, right? Because we're looking for a 1 to begin with. If you get a 0, that's not the bit we're looking for to start with, right? So we just go to our start here. Okay, what if, we're still on resetting, we get our detection, and then we get a 1. Where will we go? Yeah, we go to B because it takes a 1 to get to B. So you see, we go to 1 or go to B when it's a 1. Okay, so what you see right here in black, green, and red, that's the state diagram for this sequence detection example for resetting. Okay, so any questions on how we got the red or anything else? Okay, so now in orange, we'll do the non-resetting. Okay, so we have a detection, and let's start with a 1. Okay, we have a detection, and now we get a 1. And we're doing non-resetting. So I could include prior bits. It'd still be B, right? Because using prior bits isn't going to help us any because we're looking for a 1, 0 to start with, and these are all 1s. So yeah, if it's non-resetting and you get a 1, you're going to go to state B. But if we get a 0, and this is what was, this is what was, I forget your name. Is it Tyler?
Yeah.
What Tyler was referring to earlier is that if it's non-resetting after detection, if we get a 0, do you see why we go to C? Right? Because if it's non-resetting, I can include a prior bit. So I would include this 1, 1, 0, which is the first 2 bits of the sequence I'm looking for. So if we got a 0 after the detection, we would go to C because it takes a 1, 0 to get to C. All right, so What you see in black, red, and orange, that would be the state diagram for the non-reset. Okay, so again, the difference between the two is what happens after you have a detection. Before detection, the state diagram is the same for both. See, that's the biggest mistake people make with these when they're doing state diagrams. Is, they're thinking, there's some difference between the two over here, when no, that's all the same. It's not until you get a detection that there's any difference between the two. Okay. Okay, so if you understood this example, what you have to do for lab 6, now granted, I think these type of state diagrams for sequence detectors, they're a little tricky. If I don't write down what it takes to get to each of the states, I find myself, second guessing all the time. Now, again, some people can do it without writing anything down. So if you can, fine. But I think most people, this helps. I know it helps me. Okay, so what's left is, I just want to show you a couple of things on Canvas that have to do with Lab 6. And also, I just want to kind of summarize what the next 3 weeks, what we have left in this class. Okay, but before I bring down the screen and turn on the projector, any questions up to this point? Everybody's good? All right. All right. So let's turn on the projector. Come on. Oh, yeah, here it is. Of course. We should shut the lights on. Okay, so this is the activity universal tip register, just like the one we were talking about earlier. The only difference between this universal ship register and the one we were talking about earlier is that this one does have inputs DR in and DL in. So, just like we talked about in the first couple of examples, that's where the data coming into the ship register is, right? DR for the right ship, DL for the left ship. So you have those inputs, you have your Q output, here's your load, which is the same as, the input to a register, the D input. You got a select line that's 2 bits, and it's the same options here, hold for zeros. Now, parallel load is the same thing as just a load. Right shift, left shift. You're told it's rising edge trigger. Okay, so the 0 to 1 transitions of the clock, that's what's important. Shift registers are always synchronous. In fact, registers are always synchronous as far as their, when their outputs will change, unless the only exception to that is if you have like an asynchronous reset or asynchronous set. Let's see, what else do we have? And then also note that we're told the initial value of D out is a hex 45. Okay, so when you do these, there's 2 examples here, 2 timing diagrams. When you do these and you look at, the rising edge of the clock, first you got to look at what the select is, because that's going to tell you what operation it is, whether load, shift right, or shift left, or a hold. And then, you just got to figure out what your output would be at that point. If it's loading, it's just going to take this data on the D load and transfer it to your output. If it's shifting left or right, then you're going to have to look at, if you're shifting right, you're going to have to look at DRN to see whether it's a 0 or a 1. If you're shifting left, you'll have to look at DLN to see if it's a 0 or 1. And since you're given values in hex, right? Your initial value 4 or 5 hex, and you should put all your values in hex. What I find the easiest, and I think what most people find the easiest, is that if you've got something in hex, convert that hex to binary, then do the shifting in binary, and then convert back to hex to put it in hex on the time diagram. So there'll be some cases where you have to, do some conversion between base 2 and base 16, and also the other direction, the 16 to base 2. I think that's all I wanted to mention about this. Do you have any questions about, what you have to do, or any questions again about what these different operations mean? So it's just practice on what we talked about earlier about the shift register. Okay, the next thing is I just want to, this is lab 6. And lab 6, you can see it's a resetting Moore type FSM sequence detector. And we want you to be able to detect 2 sequences with your FSM. So one sequence is 011101, and the other sequence is 011001. And this first sequence is to be detected when a button is pressed. Okay, one of the buttons on your basis board is pressed. The other is to be detected when that same button is not pressed. And if you look at these 2 sequences, they only differ by 1 bit. Okay, only the 4th bit is different. So before you, create a new project to, do this lab in, the first thing you should do is a state diagram. And actually, there's 2 different approaches that I've seen that has worked for this. You can do a single state diagram, okay, for both sequences. Again, they only differ by 1 bit. Or you can do 2 separate state diagrams. One state diagram for one sequence, another state diagram for another sequence. I've seen people do it both ways. When I did it, I just did 1 state diagram. But again, it's really personal preference whether you want to do 1 state diagram or 2, both work. Now, if you take a look at the modules, we got 4 modules. The only one that you're creating is the FSM. So you see this one right here is the one you're creating, right? So, you create your state diagram, and then from that state diagram, you put it into that format that I showed you for FSM's last class. Right? Remember, it's very cookbook to go from a state diagram to that FSM modeling that I gave you with that example of a counter, non-sequential counter. So that's what you need to do. These 3 other modules are given to you. Okay, Dr. Mealy designed these modules. One's a sequence driver, one's a clock divider, and the other one is this BC deck. These files were written in VHDL, okay, not Verilog or System Verilog. And in fact, if you look on Canvas, where these files are located, module down by the resources. Yeah, right here. Lab resources. So right where the universal seg text was, these are actual files. They're VHDL files. So the suffix is .vhd. So here's the sequence driver, the clock divider, and the BC deck. So you can just download those and put them right into your project. And Vivado can run mixed languages. Okay, so you can have like Verilog with System Verilog or System Verilog with VHDL, and it will all work. So you're just going to use these files as is, although there is one modification you'll have to make to the clock divider module. And what do clock dividers do? Because we talked about a clock divider last class. What does a clock divider do? Like you put in the 100 megahertz into it, and what do you get out? A slower frequency, right? A slower clock. So that's exactly what this is doing. It's taking in the 100 megahertz from the board, and it's going to make it a lower frequency. Okay, but there is a modification you'll have to make that I'll talk about when I show you a video in just a moment. Okay, but getting back to that diagram. Getting back to this. Okay, the clock divider, like we said, is going to slow down the clock. Now notice that BC deck, this module of Dr. Mealy's, it takes the fast clock. So you see, this is the 100 megahertz, and it bypasses the clock divider because his BC deck needs the fast clock in order to work right. But the slow clock, what's coming out of the clock divider, that's what's driving, or that's what's running the sequence divider and also your FSM. Okay, so the FSM and sequence divider, that's operating at the slower frequency. BC deck is operating at the fast frequency. And if you take a look at the sequence divider or driver, the inputs are switches, okay, 8 switches. Okay, so you're going to have 8 switches on your board, and the data that you set the switches to is going to be inputted to the sequence divider or driver. I keep saying divider when it's driver. And then the sequence driver, it just has a single bit output that you're going to connect to the X input of your FSM. So what this sequence driver is doing, it's taking the 1s and 0s that you set the switches to, and it's putting those 1s and 0s all on one output. So coming out of your sequence driver is going to be something just like this. It's just going to be a string of 0s and 1s. And you know, the particular string you're going to get is going to be determined by the position of the switches that you set on the board. Okay? So that output of the sequence driver, that goes into your FSM. So, you know, that's where you're going to design your FSM to look for those sequences we talked about. Okay? And then you have this BC deck. And BC deck, other than this clock input, the only other input is a single bit input that's connected to your FSM output. Because just like in that example, the Z output, you're going to have a Z output of your FSM where that output is a 0 until you detect the sequence, right? So the output of your FSM only changes to a 1 when you've detected a sequence you're looking for, okay? And when a 1 is at the input of this BC deck that Dr. Mealy designed, and Dr. Mealy designed this module so it gives 2 messages. Okay, if there's a 1, meaning you have a sequence, it's going to message cool, okay, the word cool. If you don't have a detection and it's a 0 in Dr. Mealy's module will display crap. So students refer to this as the cool crap module. Okay, why Dr. Mealy chose those words, I don't know. But you know, Dr. Mealy, it's Dr. Mealy. But anyway, that's what this module does. Let's see, what else? Oh, I want to show you a video of this working, but any questions up to this point? Again, you're only doing one module. This is the module you're creating, the FSM. Well, along with connecting it up. So you'll have also a structural model to make the connections. But these 3 other, like I said, are given. Okay. All right, the last thing I want to show you is a video that shows the sequence detector working. This is my sequence detector. Just so you have an idea of what it's supposed to look like. Right here. Okay, so you see the LEDs are moving. See, as an LED lights up, that's the bit that's being inputted to your FSM. And I have the switches set for the sequence for when a button's not pressed. So you see, after it goes through checking all the switches, it will change when it finds the sequence. And that sequence can be within any pattern of the 8 switches. Okay, now I'm changing it so it's not the sequence that's being looked for with the button not pressed. So you see it just stays crap the whole time because it didn't pick up the sequence. Now, this video doesn't show all the test cases. There's 4 test cases and I only showed 3. See, this is now detecting the sequence when the button's pressed. So you see once it goes through, it changes. Okay. The test case that I don't show is when the button is pressed and it doesn't detect that sequence. Okay, so when you do yours, you got to show 4 test cases. Okay, so don't copy this because this is missing a test case. But the other thing I wanted to point out in this video is just the rate of the LEDs. You see how the speed of it is, it's not too slow or too fast. It's kind of like Goldilocks speed, if you will. But the reason for that is because I went into that clock 2 divider module and I changed an integer. Okay, remember we talked about last class that in our example, there was a max count integer. And by changing that integer, you can change the divide by how much that fast clock is being cut down, right? Well, even though Dr. Mealy's module, clock divider module, is written in VHDL, same idea. There's an integer that you'll just have to go into that code and just change the integer. Okay, because if you don't change the integer, it's going to be too fast. These LEDs are just going to be racing, and every time you get a detection, it will just blink. Like there's not enough time to even see that it went to cool. You'll just see it blink really quick. Okay, so make sure that you adjust that clock divide so it's going at speed relatively close to what you see in this video. There's no one right answer. There's no one right integer value to put there. You just gotta kind of through trial and error, or you could figure it out. But you just need to experiment a little bit and get it to a speed that's reasonable, like you see here. Okay. All righty. So I think, the last thing, well, any questions on anything that I showed on Canvas before I put the screen up and turn the projector off? Because the last thing I want to do is just talk about the next 3 weeks. Just a reminder of what's left this quarter. Okay, so most of what I talk about here is already on Canvas in the syllabus, and I've talked about a little bit before, but again, I know it's a long quarter, maybe you've forgotten some of this, so let me just kind of recap what's left for the next 3 weeks. So as I mentioned at the beginning of the quarter, this is a blended class, which means, it's some in person, some, quote unquote online. So the first 15 meetings are in person. For the last in-person meeting we have is Tuesday of next week. Okay, that's May 23rd. That's our 15th meeting. And during that meeting, I'm going to talk about binary multiplication. Now, I talked about it a little bit, right? Because we talked about how to multiply by a whole number power of 2. Well, on Tuesday, we'll look at, what if you want to multiply by 3 or multiply by 7, or, some other number other than a whole number power of 2. So that's an important class because your final project individual is building a 4-bit binary multiplier. Okay, so this is particularly important for that. Also, that's going to bring up another logic device called an accumulator. Okay, because that's going to be part of your final project individual, and I'll discuss what that is on Tuesday. And then I'm going to go over in detail, what's required for the final project. And like I mentioned at the beginning of the quarter, and also what's in the syllabus, the final project has 2 parts to it. There's an individual part that's due the 19th week of the quarter, and there's a team part that's due the 10th week. Okay, and I'll talk about both of those. What the criteria is, what the grading criteria is going to be, and all that kind of stuff. So again, Tuesday is really important. Every class is important, but in particular, Tuesday of next week is important. Thursday of next week, so a week from today, that's an open lab. Okay, open lab means you don't have to be here. It's just the lab's going to be open. I'm going to see if the ISAs can be here at least a part of the time. I'll either be available on Zoom, or if I'm on campus, I'll be at my office. Okay, so that's a class to either catch up or get ahead. So remember, Lab 6 is going to be due Friday of next week. So maybe some of you will need that time to get Lab 6 done. And if you're done with all your labs, you could get an early start on the final project, either the individual part or the team part, or both for that matter. It's up to you. Okay, and then like I said earlier this quarter, the last 2 weeks, we don't meet for class. There's no lecture. There's no tests, no activities, no anything. It's just the last 2 weeks is time devoted for you to work on your final project, which again has 2 parts. So, the reason I'm giving you this time is because, it's some work. It's not time to take off and then on, Friday, the last class day, oh, I've got I got a final project to do that has 2 parts. If that happens, you will not finish. Okay, you got to start and do this in a timely manner. So the due dates that are left, Lab 5 is due tomorrow, Lab 6 is due a week from tomorrow, right, which is Friday, May 26th. The final project individual is due the Friday of the 9th week, so that's June 2nd. And then the final project team is due the last class day. That's the last Friday before finals week. And then there is no final exam. Okay, so once you've finished your final project and you've turned that in, both the individual and the team, you're done with this class for the quarter. Okay, there's nothing to do for this class during finals week. You can concentrate on your other classes. Okay, I know some instructors that teach this course, they do a final project and a final exam, but I think that's too much. Okay, you've had a midterm. That was kind of like the theory evaluation. The final project is more the application evaluation, and how well you're modeling in Verilog. Okay, so do you have any questions? Now, like I said, I'm going to go into more detail on Tuesday about the final project, but any questions about anything we talked about today or any day else that you have questions about? No? Okay, so the rest of the time is yours. Make sure to do the activity for today first, and then once you're done with that, if you want to stay here, work on labs, that's fine. If you want to go somewhere else, that's fine. It's up to you. And Blake should be here in about 45 minutes.